Hey guys, Miss Peterson here, and today we're talking about electrolysis and electrolytic cells. Electrolysis is exactly what it sounds like. Lysis, you remember from biology, it means to break something apart. An electro refers to electricity. Okay, the literal transition is split with electricity. Basically, it's applying electricity to some molecule, like water, we can do it with water, to break it into its parts. We can apply an electric current to water in order to split it into hydrogen gas and oxygen gas. And that's a really cool experiment to do because you can actually see that you'll get double the amount of hydrogen gas as oxygen gas, as to be expected from the chemical formula, H2O. So, electrolytic cells are thermodynamically unfavorable cells, okay? They're used to separate ores or plate out metals, okay? For example, we all use aluminum foil. When you get aluminum out of the ground, that's where you find aluminum, it doesn't come out as shiny aluminum foil. It comes out normally as aluminum oxide. So we have to separate that into the aluminum and the oxygen gas. And we use that using an electrolytic cell. Okay? So we do need to be very clear on the differences between voltaic cells, which we've been talking about in the last 3 videos, and electrolytic cells. The key difference here is that voltaic cells are thermodynamically favorable, okay? They happen on their own. Electrolytic cells are not. You have to force an electrolytic cell to happen using a battery, okay? The way I remember it is a voltaic cell is a battery, an electrolytic cell needs a battery, okay? Another important distinction is that voltaic, we had our 2 half cells creating our cell with that salt bridge. An electrolytic cell is just in one container. You'll see this in a mini lab that we're going to do later. We can still remember NOx and a red cat. An anode is where the oxidation occurs and reduction occurs at the cathode. But the polarity of the electrodes is reduced. Normally, anode in a voltaic cell, the anode is negative, sad, onion, anion. But in an electrolytic cell, the anode is positive and the cathode is negative. So you can kind of remember EPA, electrolytic, positive anode. However, electrons do still flow from the anode to the cathode, which we remember using fat cat. And electrolytic cells, they normally use inert electrodes like platinum or graphite. Graphite, the same graphite that's in your pencil. You'll see that in a lab that we're going to do later. So, for example, you can kind of see this picture here. See these little strings of metal, it looks like? That is solid tin being pulled from the solution through electrolysis, okay? From the tin chloride solution. So, let's do an example. One of the most common applications of this is to plate jewelry. Okay, so if we want gold earrings, big gold earrings, we're not going to make them out of solid gold. One, solid gold is kind of soft, so it would be kind of fragile and malleable. We wouldn't want that. And second, that's expensive. So we plate a cheaper metal with gold to make our 14-karat gold earrings. So we're going to sketch a diagram of a cell that could be used to electroplate a copper ring with gold. We're going to have one compartment, a battery, a bar of gold, and the copper ring. Identify which metal will be the anode and which will be the cathode. Choose a solution, battery, flow of electrons, write the reactions. Okay, so I'm going to scroll past that description so I have a place to draw it. Okay, now let's start with what we know for sure. We have one container. Okay. There's our container, and they told us that we have to use a gold bar and a copper ring. So those are actually going to be our two, our anode and our cathode. We'll talk about which is which. Okay, I'm not a very good drawer, so let me label that. That is a copper ring that we want to plate in gold. And then here is our gold bar, which can be used to supply the gold ions that will go onto the copper ring. So now the copper ring, we want the copper ring to get gold solid formed on it. Okay, so we know we want to form gold solid. we check out our table of standard electron potentials, and we see that that reaction is actually a gold 3 plus ion plus 3 electrons forming that gold solid. Now, is that oxidation or reduction? Well, the gold is gaining electrons, and if you remember oil rig, okay, reduction is gain. So this is our reduction reactant. The gold is being reduced onto the copper ring. And red cat reduction occurs at the cathode. So we know our copper ring must be our cathode, which means our gold must be our anode. And an anode is where our oxidation occurs. So that's the opposite of the reduction reaction. The gold solid is reducing or being oxidized into the gold and the electrons. It is losing electrons. Oxidation is loss of electrons. Okay, so you can kind of picture that in solution. We have our gold ions breaking off from that gold metal, and then it's gaining electrons over here to form back into the solid. So the electrons must be being removed from the anode and getting placed in the cathode. And then there is our battery. Okay. And electrons, typically we have them flowing from negative to positive. So this electrolytic positive anode, okay, EPA. So this is actually going to be positive, which makes sense because you're removing electrons from it. And our anode is going to be, or our cathode, the copper ring, is going to be negative. Okay, so we got our flow. Oh, we also need to decide what salt we are going to be putting in there, because we can't just have gold ions floating in solution. That's not super realistic. We would likely use salt that we know will dissolve. So what's a salt that always dissolves, that has gold in it? Gold nitrate. So we'd probably use gold nitrate in solution, because nitrates, if you remember from solubility, always dissolve. Okay, so that's how we would plate gold onto a copper ring. Okay, cool? Okay, cool. So we do need to be able to predict the products of electrolysis. Sometimes it's really easy. Sometimes we don't have aqueous things, and you just have a pure molten ionic compound. In that case, the cation, the positive one, will be reduced. It'll go toward neutral. The anion, the negative one, will lose electrons. It'll go up. If you look, for example, at NaCl, okay, well, that is formed of an Na plus ion. That one will be reduced, okay? So it will turn into, oops, the cation will be reduced. So it will lose an electron. I am confusing myself here. Okay, it'll be reduced. It'll gain electrons and go down in charge. So we have our Na plus and an electron forming our Na solid. Okay, where the chlorine ion, that will lose an electron. Okay, and it will go up in charge to be chlorine solid, probably, and then an electron. Or chlorine actually is a gas, it'd be Cl2 gas. Okay, and an electron. Okay, cool? Okay, cool. But we run into a problem when water is present. So if we have water, then we need to figure out if the ions or the water is going to reacting. So we can look at the standard reduction potential and figure out which one is more likely based on just what their reduction potentials are. But the easiest way to remember it is group 1 and 2. So those are our alkali metals. They like being ions, so they're not going to be reduced in an aqueous solution. Water will be reduced. And no polyatomic ion will be oxidized. Water would be oxidized instead. Okay, So if we look at this example, PbI2. Well, that's no alkali or alkali earth metal. So we can predict that our Pb2 plus ion, okay, we have that, and then we have two I minus ions, okay, they are going to form their compounds. So the lead is going to gain 2 electrons and be Pb solid, while the iodine is going to lose an electron and be iodine solid. Okay, and iodine's a diatomic, so it is I2. Where sodium is an alkali metal and sulfate is a polyatomic ion. So instead, it is aqueous, so there's also water. The water will be both reduced and oxidized. Okay? And you can see when water is oxidized, it forms oxygen gas. When water is reduced, it forms hydrogen gas. So in a situation where we have an alkali metal and a polyatomic ion, we're just going to be producing the products of water, our H2 gas and our O2 gas. Okay, cool? Okay, cool. Now, calculating the electrical energy needed for electrolysis. We're going to be using Faraday's Law. You can memorize this formula, that the number of grams plated, gold or copper, whatever you're looking at, equals the current times the time times the molar mass divided by the number of moles of electrons in Faraday's constant. That's really complicated to me. I'm going to show you guys how I solve it using dimensional analysis. But if you just want to memorize a formula, you can totally memorize this formula and it won't let you down. Okay? So time, remember, needs to be in seconds. Current, amps, which you might have learned from physics class, an amp is actually a coulomb per second, and that's going to be really important to remember, that amps is coulombs per second. So let me show you guys an example of this. How many minutes must a current of 5 amps, okay, just like I rewrite molarity as moles per liter, I'm going to rewrite amps as coulombs per second, must be applied to a solution of silver plus to produce 10.5 grams of silver metal. So it says you're taking that silver plus, adding an electron to it to produce your silver metal. Okay? And we want to produce 10.5 grams of that, which means we need we need moles. Okay? I know how many moles of electrons I might need. I need 1 mole of electrons for each mole of silver ions, but I only have my grams. So how do I convert from grams to moles? Molar mass, yeah. Okay, so I'm going to do this and kind of walk you through it. So we have 10.5 grams of silver that we want to produce. Okay, I need to convert it to moles. So I use the molar mass from the periodic table. 107.87 grams of silver is 1 mole of silver solid. Sorry, we're talking about silver solid here. Okay, now I knew for every 1 mole of silver solid that I need to produce, I'm going to need 1 mole of electrons. Okay, and I know that's 1 over 1. It seems silly to include, but it won't always be 1 to 1. You might need more than 1 mole of electrons. Okay, now how many, it's asking us for minutes, so I'm trying to get to minutes here. Now, I know that 1 mole of electrons has a charge of 96,500 coulombs. That's Faraday's constant. It's on your equation sheet. Don't gotta memorize it, but that's that. Now, we're getting closer. Ooh, no, low battery. So, I know that I'm going to have 5.00 coulombs every 1 second. Okay, that's from that current 5 coulombs per second. And then it's asking me for minutes, so I need to convert from 60 seconds to 1 minute. Okay, so a long dimensional analysis problem. Check it out. Make sure it makes sense. Moles of silver, moles of silver, moles of electron, coulombs, seconds. I'm left with minutes. Everything makes sense. I grab my calculator and I plug it all into my calculator. 10.5 times 96,500 divided by, put all the bottom in parentheses, 107.87 times 5 times 60. And I get 31.3 minutes. 31.3 minutes. Okay, cool. Okay, cool. Now, typo in it, I solved it out 1,000,000 times, and it never made sense. So what we're going to do is I'm going to change the numbers to make it make sense. I even asked people if they could help me, and we decided that the problem was written wrong. So I'm going to change this 0.0066 grams into 3.639 grams. Yes, I know that's nothing like it, but we're going to make the problem make sense. So, a solution of a platinum chloride salt is subjected to 20 amps of current for 1 hour. During this time, 3.639 grams of platinum is plated. What is the formula of the platinum salt? Okay, so we have our platinum chloride. That's PtCl something. We know chlorine's 1 minus. So we need to figure out how many electrons were transferred here. Okay, how many electrons were transferred? So for every gram that was plated. So first, let's go ahead and convert it into moles because I know I can work with these in order to get my moles of electrons. So if I have 3.639 grams of platinum, okay, the molar mass of platinum from the periodic table is 195.08 grams per 1 mole. You plug that into your calculator, and you get 0.0186. 1865, so I'll say 187 moles. Okay, now let's figure out how many moles of electrons I had in that 1 hour. So 2 amps, remember, is coulombs per second. In 1 hour, I don't know off the top of my head how many seconds are in an hour. You might. I'm just going to put it all into my problem. I'm going to use this little line as my line. So 1 hour, I know that in 1 hour there are 60 minutes. I know in 1 minute there are 60 seconds. Now, if that was going on for an hour, I know that I was getting 2 coulombs each second. Okay, that is from the current. Now, I know that 96,500 coulombs are 1 mole of electrons. Okay, so I got 1 hour times 60 minutes times 60 seconds times 2 divided by 96,500. And when I solve that out, I get 0.0746 moles of electrons. Okay, so 0.0746 moles of electrons plated, that many moles of platinum. So for each 1 mole, how many electrons were there? Well, you just set it up as a ratio. So I take my 0.0187, divide it by my moles of electrons. Take my moles of electrons, 0.0746, divide it by my moles, and I get, I'm having an issue, 0.0746 divided by 0.0187. Okay, and I get 3.99, which I can assume that means 4 electrons were transferred in order to switch that platinum ion. So we had platinum of some ion plus electrons, some number of electrons going to my platinum solid. How many? It was 4 electrons, which means the charge on my platinum must have been 4 plus. meaning my formula must have been PtCl4. Okay, cool. Okay, cool. So let's just talk about some applications. Again, the main one is the one that we use to produce aluminum. Okay, they do that in a mixture of aluminum oxide and sodium aluminum hexafluoride. Okay, and then they have the graphite rods. They form the carbon dioxide, and we get the molten aluminum. Very good. But electroplating, very important. And that it's not just in jewelry. Any cars you see on like the rims of the tire being chrome, that's all been electroplated. We also know that things corrode. Rust is just a process of oxidizing a metal, but we normally plate something on there that is like what is it? Titanium. Titanium doesn't corrode as easily as other metals, so we can just plate it on there and protect the metal on the inside from that corrosion. Okay, so that's electroplating and electrolysis. Go ahead and do the self-check on your own, and we are done with our series of electrochem videos. Okay, cool? Okay, cool.